Okay, looking again at the trapezoidal graph of y equals x cubed plus 5 on the interval from x equals 1 to 1.5 by a step of 0.1. We got all the values, and here's the trapezoidal approximation graph, at least up from 1 up to 1.4, from x equals 1 to x equals 1.4. Now, we want to make a few comparisons. Okay, we want to calculate the actual slope, which we calculate by yPrime. Now, of course, we're assuming that we understand, whether we understand the details of how you calculate the yPrime function, that there is a yPrime function that tells us what the actual slope is at a point. So the actual slope, and I really should relabel this, and let me go off screen for a second. Okay, I've just labeled this actual midpoint slope. It's the slope at the midpoint of each trapezoid. So we have this yPrime function, which for this function is equal to just 3x squared, 3 times x raised to 1 lower power. And that's actually the rule that we're using to calculate yPrime. I told you it was simple. Of course, if you have the calculus, you understand that, and you know what that rule is. But we calculate the actual slope that corresponds to this function at the midpoint of each interval. And we expect that that average slope should be pretty close to the, or that midpoint slope should be pretty close to the average slope on the interval. It should be closer than the actual slope at the left or right hand ends of the interval, since the slope that we calculate for the trapezoidal approximation graph, our average slopes that are indicated here, are averages over the entire interval. We expect that those averages are going to be closer at the middle than they are at the endpoints, and that should be for fairly obvious reasons. Especially if you've had the calculus and thought about these things, but many calculus courses are taught so that you don't even think about that, or that you do it very much in passing and concentrate just on remembering a few simple rules. Okay, a real calculus course is going to address these issues as well as interpretation and so forth. Okay, so we calculate the actual midpoint slopes, and very easy to calculate these, 3x squared. Here are our x values, we square them and multiply by 3. Then we compare that with the average slope that we got from our trapezoidal approximation graph, and we see that these numbers are always very close. Now you should look at those numbers and see how close they are. 3.31 is really close to 3.3035. The difference being just negative 0.0025. Now the difference in every case for this function is 0.0025, and it's a negative, meaning that the trapezoidal slope is actually greater than the midpoint slope. And let me rethink that for a minute. Clearly the trapezoidal slopes are greater than the actual slopes, and these differences, trapezoidal slope minus actual slope, should all be positive. Had a similar error over here, and we'll talk about that and make sure I didn't make a mistake by removing those negative signs, but we'll talk about that and see why that occurs. Okay, so the point now is that for this graph, the trapezoidal approximation graph slopes are always a little higher than the actual midpoint slopes. Okay, we're not going to go too deep into discussion of why that's true, but we might do a little addendum where we discuss that. Then, okay, let's just see what kind of errors we have here. This is 0.0025. That's 1 part in 400, or that's 1/400th, and the actual slopes are like 3.31, yeah, and so forth. So typically these are on the order of a 10,000th of this, okay, or a 1,000th. Sorry, but somewhat less than 1/1000th of these numbers. Take 1/1000th of this number or this number, it's more than twice as great as this number. Down here, closer to this number. And you should be able to do that without reaching for a calculator. You should be able to estimate that sort of discrepancy and see that this is 1 part in like less than 1,000. actually less than 1 part in 1,000. Down here, less than 1 part in 2,000. Okay, now, and that's a very small discrepancy. Okay, now trapezoidal graph approximate accumulated area, and we just copy our accumulated areas, and I don't have this whole table here, but these are the accumulated areas that we got from the trapezoidal approximation graph. And then we have this fancy capital Y function, which is our antiderivative. And it's actually really pretty easy to calculate the antiderivative of this function. The rule basically here is you just raise this power by 1, and then you divide by that new power. And then you have 5 times x to the 0. You raise that to the first power and divide by 1. You get x to the 4th over 4 plus 5x. And that's just the function that was evaluated to get the actual accumulated area. Now there's a little more to it. I had to subtract off the area that would have accumulated between 0 and 1. And we don't need to worry about the details of that. I'm just pointing that out to say that the calculation is pretty simple. And really learning the little bit of calculus you need to do that for power functions and polynomials, you can learn it in an hour. You don't need to know it to understand what we're talking about here. Okay, what we're talking about is discrepancies between the trapezoidal approximation graph and these functions that you might or might not understand. Okay, this is the function that we use to calculate the actual accumulated area, and these are the results that we get. And here are our trapezoidal approximation graph results. Now, you see a couple of things. If we do the accumulated area minus the actual, okay, trapezoidal approximation accumulated area minus the actual accumulated area. Let's see if I got that right. Which is bigger, this or this? Well, let's see. It looks like this is bigger than this, and it looks like this is bigger than this. So when I do that, I do get a minus sign, okay? The trapezoidal approximation graph is less than the actual area, and that's just not right. Okay, because of the concavity of this thing, the actual area has to be less than that of the trapezoidal graph. So let me see what I've done wrong here. Okay, don't know that you noticed the error, but if you refer back to the values that we actually got here, and actually the values that I've written down here, we see that I just mislabeled these 2 columns, and if you probably noticed the change in these labels. This is the actual, this is a trapezoidal graph. So now that reconciles. When I subtract the actual from the trapezoidal, I get a positive number because the trapezoidal area is greater than the actual area because the graph curves like this. The actual graph curves like this. It's always below the trapezoidal approximation except at the right and left endpoints of the trapezoids. Okay, well, in any case, there are our trapezoidal minus actual areas, and we notice that in contrast to these numbers that are always the same, the trapezoidal slope minus actual slope at midpoint, the difference is always the same, and that just goes back to the fact that this is a 3rd degree polynomial, and 2 derivatives give us a 1st degree polynomial, and that gives us the constant change in the 2nd degree polynomial, which is the derivative, and you don't need to understand any of that. But if you know the calculus and know it pretty well, you would probably understand what I just said, so I mentioned it. Okay, again, trapezoidal area minus actual area is always positive because the trapezoidal area, the trapezoids always go above the curving graph, the way this graph curves. Graph curves like this, goes the other way. Okay. Now I also okay, well let's back up. Okay, we see that these numbers keep getting bigger and bigger, and there's a reason for that. Remember, these accumulated areas on the trapezoidal graph are obtained by adding successive areas of trapezoids, so that as we accumulate error from one trapezoid to the next. In calculating the area of each trapezoid, we got a little error relative to the actual area. And when we accumulate those errors over several trapezoids, naturally we get an increasing discrepancy. Now it's worth looking at the discrepancy compared to the actual areas or the trapezoidal areas. And I got one more labeling thing, hang on. Okay, the big fancy Y was over here. You can see the wet spot where I've corrected that. It's over here because obviously that's what we use to calculate the actual area. So when I reverse these labels, I should have put that there. Okay, if we look at the discrepancy here between the trapezoidal approximation graph and the actual, we see that this discrepancy continues to increase. It would be interesting to look at this discrepancy as a percent or proportion of the actual accumulated area. Okay, so the actual accumulated area is like 0.6. This is like 0.0005. That's not much different than 1/1000th of this. 1/1000th of this, and you should be able to see that pretty easily. Put 3 more zeros in here, and it's pretty close to this number. Put 3 more zeros in here. Well, actually, move the decimal point over 3. You're going to add 2 zeros in front of it. You're going to get something pretty close to this. So it looks like this discrepancy is a fairly constant multiple of, or fairly constant proportion of the actual area, and it's around 1/1000th. A picture helps us understand these comparisons. For the slopes, we have a trapezoid here. We have a curve, and the curvature is exaggerated, much greater than it is for the graph that we looked at on the intervals that we were using. But we have the trapezoidal slope, the straight line slope from this point to this point, and we have the curve. And if we draw a tangent line to that curve at its midpoint, then the slope of that tangent line ought to be pretty close to the slope of the curve. If this was a quadratic function, they would be identical. Okay, if it's a polynomial that's not quadratic, they aren't going to be identical, except maybe for some very special cases. Okay, so that's what we're saying when we say that the discrepancy between the trapezoidal approximated slope and the actual midpoint slope is about 1 part in 1,000. That's for this interval from x equals 1 to 1.4, and with a step of 0.1. Okay, now the right-hand endpoint, well, the right-hand endpoint is here. And clearly the slope of the tangent line at that point is going to differ more significantly from the slope of the average slope, the slope at the top of the trapezoid, than the tangent line at the midpoint. And let me draw that. So here I've sketched a tangent line to this exaggerated curve. Okay, the curvature is not that great, but it's very clear that the slope of this line here at the right end point differs very significantly from the slope of the trapezoid, whereas the slope of this tangent line doesn't differ in any way you can really pick up with your eye. Okay, even on this exaggerated interval with exaggerated curvature. So that kind of explains the difference between the 7 parts in 100 discrepancy that we get between the slope at the right end point and the trapezoidal approximation graph slope, and as compared to the discrepancy of 1 in 1,000 to 1 in 2,000 between the slopes of the trapezoid and the midpoint for the actual curve. We can also see from the picture how the actual curve lies below the trapezoidal approximation, so that the area of the actual curve, the accumulated areas in the areas, are going to be less than those of the trapezoidal approximation. And it looks like maybe we got a 5% discrepancy here. This is an exaggerated picture, exaggerated from the 1 in 1,000 discrepancy that we have here.